Now it's your turn. 3 labs will turn these ideas into working code and hand traces. Lab 1 is the big one. You will build AVL insert yourself with all 4 rotation cases from the pseudocode template. Your job is to implement this function. It takes a node and a key and returns the new subtree root. Insert the sequence 50, 25, 75, 10, 30, 60, 80, 5, one key at a time. After each insert, print the in-order traversal and every node's height. Then confirm that every balance factor you print stays within -1, 0, and +1. One tip: write the left rotation and the right rotation first, and test each one on its own with a 3-node tree before you wire them into AVL insert. That keeps rotation bugs separate from insertion bugs. Give it a real try before you look at the solution. Try Lab 1 on your own first. Then let us walk through one solution together in 3 parts. This is the full AVL insert function. It takes a node and a key, and it returns the new subtree root. The base case: if the node is null, we make a new node here and return it. That part is the plain binary search tree insert. If the key is smaller, we insert into the left child and store the result back. If it is larger, we insert into the right child the same way. If the key is already here, we just return the node. No duplicates. Now we come back up. We recompute this node's height as 1 plus the taller of its 2 children. And we read the balance factor into B, F, that is the left height minus the right height. The left case: if the balance factor is greater than 1 and the key went to the left of the left child, the heavy path is a straight line. One right rotation fixes it, and we return the new root. The right case is the same idea on the other side. Balance factor less than -1, and the key went to the right of the right child. One left rotation fixes that one. The left-right case: the balance factor is greater than 1, but the key went to the right of the left child. That is a zigzag. First, we rotate the left child to the left. That turns the zigzag into a straight left-left shape. Then we rotate this node to the right and return the new root. The right-left case is the zigzag on the other side. First, we rotate the right child to the right. Then we rotate this node to the left. And if none of the 4 cases fired, the node was already balanced, so we return it unchanged. This is the exact function verified in the course code. Check the run log to compare your printed heights against a known good build. Lab 2 builds your diagnostic skill. You will predict, then verify, every node's balance factor as an AVL tree grows. Using your Lab 1 solution, insert 30, 20, 10, 25, 5, 40, 35, 45, 1, 15, one key at a time. Before you run it, predict by hand which inserts trigger a rotation and of which type. Then print the balance factors after each insert and check your predictions. A hint: only 2 inserts in this sequence trigger a rotation, and both are the same case. Find them by tracking heights, not by guessing. Try it before you peek at the answer. Lab 2 asks you to predict the rotations before you run the code. Let's check the answer. Only 2 inserts cause a rotation. Inserting 10 breaks balance at key 30. That is an LL case, fixed by a single right rotation. Inserting 1 breaks balance at key 10. Again an LL case, again a single right rotation. The final table confirms it. The root is key 20, with height 3 and balance 0 perfectly even. Every other insert fits without trouble. Across the whole tree, each node's balance stays within -1, 0, and +1. That is the AVL rule holding everywhere. Lab 3 is a challenge and a change of gears. You will extend the balance repair idea from rotations to splits, which is how B-trees stay balanced. There is no code, just a hand trace on paper. An order 3 B-tree node holds at most 2 keys and 3 children. Insert a third key into a full node, and it splits. The middle key moves up to the parent, and the 2 remaining keys become 2 new nodes. Starting from an empty order 3 B-tree, insert 10, 20, 30, 40, 50, one at a time. Draw the tree after each insert, including every split. A hint: the first split happens on the third key, 30, a full 2-key node with no room left. Notice how the split moves the middle key up, just like a rotation moves the middle key up in the zigzag cases. Same intuition, different mechanism. Try drawing it first. Lab 3 is a hand trace with no code. Try drawing it first, then compare with this. Insert 10. The tree is a single node holding 10. Insert 20. It joins the same node which now holds 10 and 20. An order 3 node can hold 2 keys. Insert 30. Now the node would hold 3 keys, but 2 is the limit, so the node splits. The middle key, 20, moves up to become a new root. And here is the result. 20 sits on top, with 10 on the left and 30 on the right. The tree grew a level from the top, not from the bottom. Insert 40. 40 is greater than 20, so it goes right into the leaf holding 30. That leaf now holds 30 and 40. The tree so far: 20 on top, 10 on the left, and 30 and 40 together on the right. Insert 50. 50 is greater than 20, so it goes right into the 30 and 40 leaf, which is already full. That leaf splits. The middle key, 40, moves up into the root. And now the root holds 20 and 40 with 3 children, 10, 30, and 50. Here is the key idea. 5 keys, one split and promote at 30 and another at 50, and the tree stayed at height 2 the whole time. That shallowness for free is exactly why B-trees are the disk index structure of choice. There are no rotations to implement. Just split when full and promote the middle key.